Greetings and warm welcome, friends and dear students. Today we are going to see about the slope and deflection calculation of a cantilever beam of span L subjected to an UDL of intensity W per meter N over the whole span of the beam. So here I am going to apply the double integration method to find the slope and deflection at the free end of a cantilever beam with the UDL for the entire span. So the moment at the section XX, which is at a distance small x from the free end, is minus WS square by 2, where x is the distance from the free end to a section XX to the left of free end B. Now, EI d square y by dx square is equal to minus WS square by 2. Now integrate once, you will get a general slope equation, that is EI dy by dx is equal to minus WSQ by 3 into 2. So you are getting WXQ by 6 plus constant of integration C1. So here you have to determine the constant of integration C1. Similarly, you have to go for once again the integrate the slope equation. You have to get the another constant of integration C2. So once again you integrate the slope equation. So that is EI y is equal to minus WX power 4 by 24 plus C1 x plus C2. So that is the general deflection equation. So where capital C1 and C2 are the constant of integration, these constants can be determined by using the boundary condition. So at the fixed support, when x is equal to L, both slope dy by dx is equal to 0 and deflection y is equal to 0. Apply this boundary condition in the general slope and deflection equation to find the constant of integration C1 and C2. Now, when x is equal to L dy by dx, that is slope equal to 0, I am substituting in the slope equation of general equation. So EI dy by dx, so it is 0, is equal to minus W into LQ by 6 plus C1. So if you are simplifying it, the constant of integration C1 is equal to W LQ by 6. Similarly, you have to find the constant of integration C2. So here I am applying when x is equal to L in the deflection equation. So EI into y. So y will be 0. So EI into 0 is 0. That is equal to minus W into L per 4 divided by 24 plus C1 W LQ by 6 into here x is equal to L into L plus C2. So if you are simplifying C2, you are getting the value of minus W L per 4 by 24. So C1 is W LQ by 6 and C2 is equal to minus W L per 4 by 24. Now I want the deflection of the free end, that is at the point B, capital B. So we have started x from the free end B. So therefore when x is equal to 0, you substitute the corresponding x equal to 0 in the slope equation. So you will get the slope at B is equal to dy by dx B suffix B or theta suffix B. So that is equal to WLQ by 6EI. So that is the slope at the free end. Similarly, if you substitute x equals 0 in the general deflection equation, after substituting in C1 and C2, you are simplifying it, you will get YB or that is equal to Y max maximum deflection at the free end, that is equal to minus WL per 4 by 24 EI, where EI is the flexural rigidity of the beam. Once the cross section is given, X small is given, you can find the flexural rigidity of the beam, and small w is the intensity of UDL per meter length, and L is the span of the beam. So this is the final conclusion of the slope and deflection at the free end of a cantilever beam, that is at B. Theta B is equal to WLQ by 6 EI, and the deflection at the free end B is equal to YB, that is equal to Y max, that is equal to downward deflection, that is Y minus WL for 4 by 24 EI. So already you know the product is called as flexural rigidity of the beam. Once Young's modulus and the cross section is given, you can get the moment of inertia, multiply with Young's modulus, you will get the flexural rigidity of the beam. So this is how you have to find the slope and deflection at any point, not only at the free end. Substitute the corresponding value of x is equal to L by 4 or x is equal to L by 2. You will get the corresponding the slope and deflection at the required points. So what about the slope and deflection at the fixed end when x is equal to L? When x is equal to L, both slope and deflections are 0. So if you are substituting the slope and deflection equation, so definitely you will get the 0 value. So this is about the calculation for the cantilever beam with the UDL throughout the beam. So this is about finding the slope and deflection at the free end of a cantilever beam. You can see is in the reverse order condition. If you put the mirror image, you will get the corresponding equation where the calculation has been done. Thank you very much for patient listening. The next video we can go for some worked out problem in the case of slope and deflection equation, either in the double integration method or the modified double integration, which is called as Macaulay's method. Thank you very much for patient listening. God bless. Valka Vaiyagam. Valka Valamudan.